Let's solve that one by separating variables now. So at first we'll solve it the hand wavy way. Then I will take the time to be a little bit more rigorous. I'm not going to talk about differential topology or infinitesimals because that's just way too beyond the scope of this course. But if you use a different notation, if you use function notation instead of Leibniz notation, it's a little easier to justify the separation of variables step. So let's do it by separation of variables first. dy dt equals t times y squared. Separate variables. What does that mean? It means get everything involving a y on one side and everything involving a t on the other side. Y comes into this equation in two ways, with the y squared and also with the dy. Think of the dy as just something involving y. T comes into the equation in two ways, with the t and also with the dt. Get all the y's on the left and all the t's on the right. Divide both sides by y squared to cancel the y squared there, and pretend, quote unquote, to multiply both sides by dt. Are we really multiplying? Not technically speaking, unless you approach this using infinitesimals or differential topology. But we do not want to think about those things. That's, this class is hard enough as it is. So there I have separated the variables. Two expressions that involve d something, dy there and dt there. You should feel the urge to integrate both sides, and you should give into that urge. As often happens, the right-hand side is easy to integrate. That doesn't have to happen. Sometimes the right-hand side could be hard to integrate. 1/2 t squared plus a constant, I'll call the constant c1. That integral is the same as the integral of y to the negative 2 dy, which equals negative y to the negative 1 plus, say, c2. Remember what your goal is. Your goal is always to solve for y as a function of t, or y as a function of x, if x happened to be the independent variable. These two things are supposed to be equal to each other. Solve for y. You could first subtract c2 from both sides and write negative y to the negative 1 is 1/2 t squared plus c1 minus c2, but you might as well just call that c3. C3 is c1 minus c2. These things are arbitrary constants, so it doesn't matter what I call them. Solve for y, solve for y. Multiply both sides by negative 1. And also y to the negative 1 is the same as 1 over y. Oops, I made a mistake. This should be a t squared. But negative 1 times c3, I might as well just call that c4. That's negative c3. I'm making these extra comments here. You don't have to when you write your homework. Almost done. Take the reciprocal of both sides to solve for y. Be careful. It's common for people to make a mistake at this point and think that the answer has got to be, I guess I take the reciprocal of that and get negative 2t to the negative 2 plus 1 over c4. No, that's wrong. Not allowed. Not an algebra rule that you can do that. For example, 1 over 1 plus 1 does not equal 1 over 1 plus 1 over 1, right? That's 1/2. That's 2. You can't break it into two fractions like that. So you need to do 1 over the entire thing. 1 over this entire thing needs to be in the bottom. It's also nice maybe to get rid of the fractions within fractions. So I'm also going to multiply the top and the bottom by 2. So I cancel the 2 down there. And I think I'll say 2c4, I'll just call it c, and I'll also put the minus t squared over here. So this is a general solution. Is it truly a general solution? Can it solve all initial value problems? Not quite. It's a general solution, again, almost. It's good enough for the most part. It does miss one solution, though. It misses the solution that's the equilibrium solution, actually, y equals 0. There's nothing you can choose for C that's going to make this function equal 0 always. So it's missing that solution. The reason it's missing is because y equals 0, when you separate variables, you'd be dividing by 0. Right there, where I'm pointing. That's the problem. That's why it misses it. However, what I'm going to show you in a few minutes, we're going to be able to get around that. Before we get around that, let me emphasize there's another way to think about solving this differential equation that avoids separating variables. See, the separating variables and the fact that it's hand wavy and we're pretending this is a fraction, but that doesn't feel right, only feels that way really because this is Leibniz notation as opposed to function notation. Let me rewrite this differential equation with function notation. Alternative approach. And if you use function notation, this hand wavy stuff with pretending that's a fraction, just that problem just goes away. Doesn't even arise as a problem. What should I call the function that is going to be a solution? I should not call it f, because this is f. This is little f of t comma y. I want to reserve the function named little f for the right-hand side of the differential equation. That is traditional. I'm not teaching you anything that's not traditional. So I need a new function name. Well, what function name should I use? I could use lots of letters, G, H, K, M, or maybe Greek letters, alpha, beta. The traditional Greek letter to use is this one, phi. Wait a minute, isn't that phi? Actually, I've never found an exception to this rule. Not that they don't exist, I've just never encountered an exception to this rule. It seems like all mathematicians say phi, and all physicists say phi. I've never encountered an exception to that rule. I'm a mathematician, so I say phi. I'm not going to buck tradition. So I asked a Greek professor, is it phi or is it phi? And he said both. Okay, got out of it. You could say phi, you could say phi, just don't say pho or phum. Phi, it's the solution function name. I can't resist saying that, I'm sorry. Oh, I have to tell a little story. This actually, phi, phi, pho, phum, the giant, Jack and the Beanstalk, actually is related to my most vivid dream in my life. When I was 5, I still remember this dream from when I was 5, okay? In a week or something, my parents were about to take me to kindergarten roundup, visiting kindergarten, before kindergarten. And I had a nightmare about it, that we were at kindergarten roundup and it was dark outside, but there was this big castle outside on the playground. I'm like, everybody's like, what? Where'd that castle come from? So we all went outside and we went into the castle and we're looking around like, what's going on? There's these big pillars. It's a huge castle, big stairway. And all of a sudden we hear phi, phi, pho, phum, and everybody starts screaming and starts to try to leave. But the door is shut. And then the giant is down the stairs. He flips on a switch and this big fan, this turbine starts spinning and sucking people into it. They start getting chopped up. And I'm like, no, I hold on to some sort of column. I'm a 5-year-old dreaming this. And all of a sudden, and this is the only time this ever happened to me in my life, all of a sudden I realized I was asleep. I'm dreaming. Like, oh, I'm dreaming. And I made myself wake up. And I've remembered it ever since. Okay. Differential equation, writing now with function notation. Phi is the function name. dy dt becomes phi prime of t. That's the left-hand side. What about the right-hand side? Ty squared. T times the function squared. T times phi of t in parentheses squared. If I write the differential equation with function notation like this, you don't even see any dy's or dt's. So how do I solve it? Effectively do the same thing I did up here, except don't write dy's or dt's. Divide both sides by the function squared. Rewrite the differential equation like this. Leave a little space. Rewrite it like that. I'm after a function phi of t, whose derivative minus itself squared is always equal to t, at least whenever I'm not dividing by 0. Those are two equal functions. I guess if I integrate them, I should still get equal functions. What should I integrate them with respect to? They're both functions of t. Now put dt's in there on both sides and integrate. But wait a minute. Is this okay? I mean, are we doing the same thing as we did up there? Yeah, we actually are. Except without Leibniz notation. How can I relate it to the Leibniz notation? I could do a substitution. I could let W, or how about Y? Actually, in the first section, I used a W. Let Y equal phi of t. It's just a substitution. For the integral on the left, it looks hard to do. And if you do that substitution, then dy is phi prime of t dt. And that integral becomes the integral of 1 over y squared dy, the exact same thing we got with the separation of variables. And it would lead to the exact same answer. It would lead to the exact same answer. When we do this integral, we could write the answer as negative 1 over y plus c2. You could replace the y with phi of t. You could write this as negative 1 over phi of t plus c2. And the goal would be to solve for phi of t in the equality between these two things. But it would be the exact same process and you get the exact same answer. By the way, the fact that I'm using the function phi, function name phi, it is actually traditional. You don't find it in all differential equations textbooks, but in many you do. It's a traditional letter to use here. That's why I'm using it. I have an ulterior motive here, though, as well. That's for the people who are going to take DiffyQ with linear algebra in the fall. In that I use this notation a lot in that class. And moreover, I also use this notation with an extra twist when I have what I call generic initial value problems. Generic IVP. What do I mean by that? I mean where the initial condition is, well, I'm not going to call it an arbitrary constant, but I am going to call it a fixed constant, y sub 0. You can call that y sub 0 because the 0 is a subscript. You could call it y0 for short, or you will sometimes hear people call it y naught. And I notice I said why not, they're not why not. Naught is N-A-U-G-H-T. It means effectively 0. Why not? Don't say why not. Why not? That's a generic IVP What I'd like to do here is I'd like to write the unique solution using the phi. I'll write it as phi of t, but I'm going to use a subscript, phi sub y naught of t, to emphasize what the initial condition is. And what's its formula going to be? It's effectively going to be this, except I'm going to solve for c in terms of y naught. Let me do a little side calculation up here. What color do we need to use here? How about purple? So again, here's my general solution that I found earlier. If I plug in a generic initial condition for y naught, and plug in t equals 0, I can solve this for c in terms of y naught. C will be 2 over y naught. And now I can plug that in here, down here, and write 2 over c, but c is 2 over y naught, minus t squared. So I'm looking right there and right there. I'm replacing the c with 2 over y naught and getting this. And let me do one more step and something amazing happens. Let me get rid of the fractions within fractions by multiplying the top and the bottom by y naught. To get 2y naught over, it's going to cancel there, 2 minus, it won't cancel there, y naught times t squared. This is the unique solution of the IVP. I'm thinking of y naught as constant, but I'm thinking of it as a fixed constant, not an arbitrary one. This becomes a function of t. And notice something amazing. If y naught is 0, if I'm on the equilibrium solution at 0, this is always 0. I get a 0 up there. So even though I can't plug in y naught equals 0 there, I can plug it in there and it works. Amazing. So this general solution here was almost a general solution. It is pretty nice. It can be used to solve almost any initial value problem. However, this form of a solution to a generic IVP does solve any initial value problem, including when y naught is 0. It's really a family of functions, one function for each value of y naught. And in Mathematica, I can animate it nicely. Here's, by the way, what DSolve value produces. It does confirm the answer that I just found by hand. This is the exact same thing as what you see here if you bring that minus sign down into the bottom of the fraction and distribute it through. I enter this function, and then what I can do here is I can plot both the function and the slope field in the same picture, and I've set it up with manipulate so that I can change the initial condition if I like. Why not? It's at -3 right now, but if I move the slider, I can change the initial condition, and I see a bunch of solutions. And notice if y naught is positive, actually, the solution right up here looks like this. And you can see when you see those vertical lines there, it seems like it's maybe got vertical asymptotes. Mathematica is just connecting the dots. Mathematica doesn't know it's got vertical asymptotes, but it actually does. So sometimes your solutions can have vertical asymptotes. If this were a model of a real life situation, you actually would ignore the parts that come on the either side of the vertical asymptotes. You would just focus on this part in the middle if it were a model for a real life situation. Okay. So again, what did we do? We separated variables in the way I showed you before to solve. By the way, do it with Leibniz notation on your homework, because otherwise you'll confuse the grader. But then I also wanted to show you that you can think about separating variables without bothering to think about Leibniz notation. And you can relate it by doing the substitution to the other method. And I also wanted to show you this notation. I did check that this worked in the other class, but with your class, I want to get onto Euler's method for our last 14 minutes. So I would strongly encourage you to check that this works on your own. Check that this solves the differential equation. The left-hand side is the derivative of this. And the right-hand side of the differential equation is this thing. T times phi of t, or phi sub y naught of t squared. Check that you get the same answer when you simplify. You'll have to use the quotient rule for the derivative. You should do that after class. That would be a very good exercise for you to do. You can also see that when you plug in t equals 0 into this expression, phi sub y naught of 0, it simplifies to just y naught because the 2's cancel. After that becomes a 0. If you take diffq with linear in the fall, this is very important to me. I use this kind of notation all the time. We end up doing some, I think, pretty cool things with it.